EVs are a thing of the past because a new zero-emission technology has just been developed. Say hello to the compressed air engine, an all-new radical design that has set out to completely revolutionize the automotive industry, and with it, the way our entire world functions. This new engine offers incredible fuel economy and practicality that outclasses both regular internal combustion engines and EVs, making it the most ecological choice of the bunch. While compressed air engines are thought of as a brand new technology, the truth is that they aren't exactly new. In fact, compressed air engines were first developed all the way back in the 19th century during the Second Industrial Revolution. The first successful compressed air engine was the Makarsky system. This was a single-stage engine in which air expanded in one piston before being exhausted. The air itself was reheated just before entering the engine by being bubbled through a hot water tank, allowing the vehicle to have improved range. Thanks to their reliability and potency, these Makarsky compressed air engines saw periodic use, most notably in trams and mine locomotives. However, there wasn't much incentive to continue developing such technologies, especially with the rise of fossil fuel-powered internal combustion engines, which were easier to manufacture, more powerful, and far more practical. As a result, the compressed air engine was largely forgotten for nearly 2 centuries. However, the 21st century has brought the same drive for innovation and advancement that the technological revolution did. By the early 2010s, companies began exploring this technology again, integrating it with internal combustion engines for maximum efficiency. Peugeot was the first company to reintroduce compressed air engines with experimental Peugeot 208 models, developed as hybrids combining IC engines and compressed air technology. This project, known as hybrid air technology, showcased prototypes capable of achieving up to 141 miles per gallon, making them some of the most fuel-efficient vehicles on the road. These hybrid air Peugeots had 2 different powertrains. One was a regular gasoline powertrain with a 1.2-liter 4-cylinder engine, while the other was a compressed air powertrain. The compressed air system consisted of a tank located below the boot, a low-pressure expansion chamber near the rear axle, and a hydraulic system with a motor and pump in the engine bay. This system balanced the 2 energy sources, completely replacing the conventional manual transmission. The compressed air tank could be recharged when the car slowed down using regenerative braking or by utilizing the engine. Additionally, the gasoline engine could compress the air, reaching maximum pressure in just 10 seconds. While these vehicles never entered mass production, they demonstrated the potential of compressed air technology, putting it back on the map. Since Peugeot's experiment, other car manufacturers such as GM have explored similar concepts. Even Peugeot, now part of Stellantis, has considered revisiting the technology. Modern pneumatic engines function quite differently from their historical counterparts. Unlike the Makarsky system, which was a simple single-stage engine, modern compressed air engines are piston-driven, much like internal combustion engines. However, they operate at significantly higher RPMs than their predecessors. One key difference is the use of springs, which help pull the piston downward when air is introduced and return it to its original position once the air is exhausted. Additionally, modern engines have eliminated the use of water in favor of standard heaters, which consistently warm the air to the desired temperature. A common question arises: how does the initial cylinder movement begin if there is no stored energy before the engine starts? The solution is simple. These engines are connected to a small electric motor that acts similarly to a starter and alternator in traditional vehicles. Peugeot implemented a similar approach, using an internal combustion engine to power the pneumatic motor at startup. The problems with compressed air engines. While compressed air technology is promising, it is not without its drawbacks. One of the most significant challenges is efficiency. Even with modern advancements, compressed air engines remain extremely inefficient. A contemporary vehicle using a compressed air engine would have a maximum range of only about 80 miles, making it impractical for even city commuting, let alone long-distance travel. Additionally, fully refilling the air tank by regenerative braking alone takes much longer than 10 seconds, rendering this method ineffective. While air is abundant and free, meticulously planning trips around refills would be inconvenient. Another major issue is power output. Pressurized air has a low energy density, meaning vehicles using this technology would lack potency compared to EVs or turbocharged internal combustion engines. Furthermore, the reliance on lightweight components results in low torque, making these engines less useful for practical applications. High RPM operation also poses a challenge, as lubricating non-liquid fuel engines is complex, leading to faster wear and shorter lifespans. Increased maintenance costs could negate any upfront savings from using compressed air technology. Safety is another concern. Pressurized air tanks can be hazardous if punctured or damaged. However, this issue is not unique to compressed air engines, as electric and LPG-powered vehicles also carry similar risks. Despite these challenges, compressed air engines still have potential. After all, EVs faced similar hurdles a decade ago, and they have since made remarkable progress thanks to continuous development. Several solutions have been proposed to address the primary issues. For example, using high-pressure air tanks could improve energy density, allowing compressed air vehicles to generate power comparable to high-revving gasoline engines. Safety and range concerns could be mitigated by designing more rigid, shallow chassis structures that double as reservoirs. Carbon fiber would be an ideal material for this purpose, as it is both lightweight and structurally strong. However, due to its high cost, thermoplastics may be a more affordable alternative. Multiple companies have already explored compressed air engine technology over the past 2 decades. One notable example is Engineer, an Australian company that developed rotary engines powered by compressed air. Their engine, known as the DiPietro motor, has been featured in various documentaries and has already seen limited use in boats and cargo carriers. Another innovator, Armando Ragucci, patented his own compressed air engine in 1990, with his prototype car achieving 60 miles per tank. So, will we see the widespread adoption of compressed air engines? The answer remains uncertain. On one hand, compressed air technology could see limited automotive use by 2030, particularly as companies seek alternatives to gasoline and lithium-ion batteries. Toyota's hydrogen fuel cell vehicles, for instance, have proven to be an interesting, albeit not widely successful innovation. However, economic and industrial factors could hinder adoption. The oil and lithium industries generate massive profits, making the shift to a free, renewable fuel source like air problematic for major corporations. History has shown that groundbreaking alternative energy technologies often face resistance. The case of Stanley Meyer, who developed a water-powered engine but mysteriously passed away after going public with his invention, is a cautionary tale. Similarly, Peugeot's hybrid air project, despite its success, was quietly abandoned over a decade ago. Although companies like Stellantis and GM have expressed interest in re-exploring compressed air engines, little tangible progress has been made beyond theoretical discussions. Ultimately, whether compressed air engines become a mainstream reality depends on overcoming technical limitations and navigating the complex financial and political landscape of the automotive industry.